Let us look at proposition number 12 of book 4 of Euclid's Elements. The proposition talks of circumscribing a pentagon on a given circle. The construction part actually involves the previous proposition as well, because we have to first inscribe a pentagon inside this circle and then proceed further. So since we have already seen this, let me just keep running it without too much of explanation. If you remember, we took a segment. First, we created a isosceles triangle where the equal angles were twice the third angle. So let me very quickly do that. See whether you can recollect my steps. Right. So we have cut it based on the condition. Okay. So let me hide off all these unnecessary details. And now the next part of constructing that triangle. So we have got the required triangle. Now we have to inscribe this triangle in such a way that it is equiangular. Again, we have seen this previously. So let's take the center first. Okay, now since we have already done it, I'll just keep taking the steps, copying one of the angles on one side of C and another angle on the other side of C. Done. Now let's do the other angle. And again mark the point of intersection of the circle with this line. Okay, now we don't require these lines now. Hide these, and now let's join these points. So now this is equiangular to this triangle. Okay, now we bisect angle D and angle C. Again, we know how to bisect it. Okay, so we have bisected it. So let's hide this. Now let's bisect D. We have bisected this as well. Now let's mark the points of intersections of these lines with the sub D and E. Okay, now let's hide off these lines. Now we don't necessarily have to connect all these points because we are not actually interested in the inscribed pentagon itself. We are only interested in the vertices of that pentagon, which we have got it. Let's join A with the center, or rather all the points that we have discovered with the center. Now at these points A, B, C, D, E, let's draw a line touching the circle at those points, the tangents. Okay, and now let's mark the points of intersections of these tangents. Okay, so now that we have marked it, let's hide the lines. Okay, now let's join these points. Okay, so we have got the circumscribed pentagon. If we have to do the construction part, that's the end of it. But we have to actually prove that this is actually a pentagon. Right? So we have to prove that it is the required pentagon. So let's do some additional construction. Let's join F and K, F and L, BF, FC, and FD. Based, and we can hide off all these other lines that are not really required. Now let's proceed. We have to prove that HK is equal to KL is equal to LM is equal to GM is equal to HG. That is one thing. Second thing is that the angles, angle H, angle G, angle M, angle L, and angle K, they are all equal to each other. So let's take it forward. Let's take FCK. We know, since this is a tangent and the diameter, or rather the radius FC is touching this tangent at the point of contact, that means it is a right angle triangle. Okay? Similarly, this will also be right angle. This will also be right angle. Let's look at triangle BFK and CFK. Let's look at these two triangles. Notice that both of these triangles are right angled triangles. So which means, and FK is the hypotenuse. So we can say FK square is equal to BF square plus BK square. Now with respect to this triangle, we can say FK square is equal to FC square plus KC square. But then left hand sides are equal, that is FK square. So we can say BF square plus BK square is equal to FC square plus KC square. Now FC is equal to BF. Why? Because they are radii of the same circle. So in the equality, BF equal to BF square is equal to CF square can be subtracted from both sides. So we would be left with BK square is equal to KC square. That means BK is equal to KC. Okay, so we have proved that BK is equal to KC. Now, again, continuing with this triangle itself, what do we have now? We have BK is equal to KC. We know BF is equal to FC, radii of the same circle, and the angle in between them is equal. That means using SAS, side angle side, we can say that these two triangles are congruent. Now, if these two triangles are congruent, then all the corresponding angles will also be equal. That means BFK is equal to KFC. And since these two are equal, let me mark that FKB will be equal to CKF. Yes. And BFK would be equal to KFC. Now, since these two angles are equal to each other, we can say angle BFC is equal to 2 times KFC, angle KFC. Similarly, we can say angle BKC is equal to 2 times CKF. Now, if you notice, these two triangles are quite similar to this. So, we again repeat the whole process. And we end up with the fact that angle FLC is equal to DLF. Angle CFL is equal to LFD. So which means again we can say angle CFD is equal to 2 times CFL. Angle DLC is equal to 2 times FLC. So let's mark that also, this one and this one. Remember, we have not yet proved that these two are equal. Okay, BFC and CFD, they are equal. We have not yet shown. Just the next step itself. Now, remember, as part of inscribing the circle, points A, B, C, D, E, the segments that we get, draw by joining them, will cut this circle into equal segments. That means circular segment BC is equal to circular segment CD. And we know equal segments have equal angles. That means angle BFC is equal to angle CFD because the circular segment BC is equal to circular segment CD. Since these two angles are equal, BFC and CFD, and these two angles are equal to each other and these two angles are equal to each other. That means each of these angles are equal to each other. So as far as we are concerned, we are interested in KFC angle and CFL. They will also be equal. So we have got these two equal angles. We have got these two equal angles and we have a common side, that is FC. Using angle side, we can say these two triangles are congruent. And if these two triangles are congruent, that means angle FKC will be equal to FLC. C. KL, and remember it also means that KC equal to CL because these two triangles are congruent. Now, that means we can say KL is equal to 2 times KC. And if we take HK, HK can be taken as 2 times BK. If we apply all this logic to including for this also triangle, then it would mean that HK is equal to 2 times BK. But we know BK is equal to KC. That means HK is equal to 2 times KC. So right hand sides become equal. So that means HK is equal to KL. Since we have proved HK is equal to KL, we can apply the same concept and show that HK is equal to KL is equal to LM is equal to GM is equal to HG. And that way we would be able to say that this is a equilateral pentagon. Now we have to prove that it is also equiangular. Now here HKL angle is equal to KLM angle. Why? Remember, we have already shown these two triangles are congruent. That means these two angles are equal. We have shown that these two triangles are congruent. That means these two are equal. Similarly, these two are equal. Since all of these angles are equal, the sum of these two would be equal to the sum of these two. Again, similarly, we can show that angle HKL is equal to KLM, which would be equal to LMG, which would be equal to MGH, and which would be equal to GHK. So that way we would have proved that this pentagon is also equiangular. So we have constructed, or rather circumscribed, a equilateral and equiangular pentagon on a given circle. So that was proposition number 12 of book 4 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail with proper references to the previous propositions. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share it. That's it for now. Bye.